Hi everyone. In today's class, we will look into nucleophilic addition reactions in aldehydes and ketones. We know that nucleophiles are negative reagents, right? So they will attack organic compounds at positive sites, right? So in carbonyl compounds, we need to look at positive sites, where these positive sites are, where nucleophiles will attack to form addition products, right? So to find the positive sites, let's look at the functional group, carbonyl group, because it is due to this functional group the reactions will take place in aldehydes and ketones. We know that from the previous video lecture, from the structure and nature of carbonyl compounds, that due to high electronegativity of oxygen, this electron cloud will displace towards oxygen, giving it a slight negative charge, and carbon will get a slight positive charge. Now we know that carbonyl carbon is a site of is a positive site where nucleophiles will attack, right, to form addition products, right? So now we know that nucleophiles will attack at carbonyl carbon. Your carbonyl carbon is a positive site, right, where nucleophiles will attack to form addition products. Nucleophilic addition reactions are of two types, right? First, where water would not be eliminated. The second type of reactions where water would be eliminated, right? No water would be eliminated. Here water would be eliminated. In the first type, where water would not be eliminated, we will look at the reactions of aldehydes and ketones with sodium bisulfite, with Grignard reagent, with alcohols, and with hydrocyanic acid, HCN. In the second type, we will look into reactions of aldehydes and ketones with ammonia and its derivatives like hydroxylamine, hydrazine, phenylhydrazine. Right? So let's look at first type of reaction. Let's look at the reaction of aldehyde, acetaldehyde with sodium bisulfite. Right? This is your sodium bisulfite. Right? Now in this compound, sodium bisulfite, your nucleophile is bisulfite. This is the nucleophile which will attack at this carbonyl carbon of acetaldehyde. So let's take the reaction of acetaldehyde, right, with sodium bisulfite, NaHSO3. This is your negative, this is your positive, this is negative, this is positive. So now since this is bisulfite is your nucleophile, it will attack at carbonyl carbon, right, to give you the compound ONA, and you get HSO3. Now in this compound, in this addition compound that has resulted, a proton transfer will take place, right? This proton will get transferred to this oxygen, and this Na will come here, right? So proton transfer will take place, right? A proton transfer will take place. Now the final addition product as a result of this nucleophilic reaction would be your OH and your SO3 minus Na plus. This is your final addition product, which we call it as acetaldehyde bisulfite compound, right? So this is the final addition product, acetaldehyde bisulfite. Now from this addition product, you can get your original carbonyl compound back by treating this addition product with dilute mineral acids, right? I'll just continue it over here. If we treat it with, say, dilute HCl, right, we will get the carbonyl compound back, right? And along with it, The other products that we will get are your, so we get, since we have a bisulfite here, we get sodium chloride, right, sulfur dioxide, and your water, right, along with it you get a water. This is one reaction. Now let's look at the second reaction with HCN. Right? Reaction with HCN take place in the presence of a base like sodium hydroxide. Right? So let's look at the reaction. Let's look at the nucleophile. Here nucleophile is this CN minus. This is your nucleophile which will attack at carbonyl carbon to form the addition product. So let's take example of an aldehyde. Right? Let's first look at acetaldehyde, and then we'll look at acetone, right? A ketone. And here we've just missed one thing in this reaction. This reaction is given by almost all aldehydes and only methyl ketones, right? So this addition reaction with sodium bisulfite would be given by all aldehydes and only methyl ketones. Methyl ketones are ketones that contain this group, right? Because ketones contain two alkyl groups, right? If one of the alkyl groups is methyl always, then it would be your methyl ketones, right? And this reaction is not given by aromatic aldehydes or aromatic ketones, I'm sorry, right? But aromatic ketones will again not give this reaction, right? Why? Possibly because of steric hindrance. Here also, why only methyl ketones? Because we know methyl group is a smaller group. If we take other ketones that has bigger alkyl groups, then that reaction would be difficult, because that will hinder or that will try to stop the approach of your nucleophile, because due to bigger alkyl groups you have more traffic, so it is difficult for nucleophile to approach this carbonyl carbon in order to attack. Same is with aromatic ketones, because aromatic ketones always contain C6H5, right? This benzene ring, we know benzene ring is a bigger molecule, right? So that is why your aromatic ketones also will not undergo this reaction because of steric hindrance, right? Where nucleophile will not be able to reach this carbonyl carbon. So this is given by aldehydes and methyl ketones, not by aromatic ketones, right? And by other ketones that does not contain methyl groups, that is those ketones that contain bigger alkyl groups. It would not be given by those, right? Due to steric hindrance, right? Now let's look at reaction with hydrocyanic acid. Reaction with hydrocyanic acid will take place in the presence of a base, right? Because base will help to generate this nucleophile. So in HCN, our nucleophile is CN minus, that will attack your carbonyl carbon to generate or to form addition compound, nucleophilic addition compound, right? So let's look at the reaction, right? Let's look at its reaction with aldehyde. This is your aldehyde, right? It will react with HCN to form cyanohydrin. The addition product here that we will get is your cyanohydrin, right? And this take place only in the presence of, you will always have a base catalyst. Base catalyst like sodium hydroxide, potassium hydroxide. This is your base catalyst, right? Your base catalyst, what it does actually, right? It will abstract this OH to form water and CN minus, with this reaction, it helps to generate nucleophile that will undergo addition reaction, or that will attack your carbonyl carbon, right, to generate this addition compound. Similarly, your ketone will also undergo this reaction right to form this cyanohydrin. Acetone cyanohydrin. This is your acetone cyanohydrin and this is your acetaldehyde cyanohydrin. And these cyanohydrins, right, this is how you will write it. Right? So this is your acetone cyanohydrin, this is your acetaldehyde cyanohydrins. Now these cyanohydrins can be used to make other compounds like your alpha hydroxy acids, right, your alpha amino acids and your alpha beta unsaturated acids. So we say that since these cyanohydrins can be used to make other compounds, we say that cyanohydrins have a high synthetic value. They have a high organic synthesis value, right? So this compound is important from synthetic point of view. When we say synthetic point of view, that means this compound cyanohydrin can be used to make other compounds, right? We'll look into some reactions where we can make some other compounds using this compound. If you take this cyanohydrin right, and if you treat it with dilute HCl, right, it will undergo hydrolysis to form COOH, right? Or let's take here, sorry, this is your H, right? This is your lactic acid, right? We know lactic acid is alpha hydroxy acid. Right, because this is your this is your carboxylic acid group, this is your alpha carbon atom, and on alpha carbon you have this OH group, so we call it as alpha hydroxy acid. So cyanohydrin is used to make lactic acid. Similarly, if you treat this cyanohydrin with ammonia, it will form amino acids. Right, if you treat it with ammonia, one atom from hydrogen will react with this OH, right, to form this compound, right? Right, it will form this compound. Now this will undergo hydrolysis to form amino acid. This is your alpha amino acid, right? And this reaction where amino acids are made from cyanohydrins, this is your Strecker's synthesis. We call it as Strecker's synthesis. Remember, right, the name of this reaction. This is your Strecker's synthesis, where you make your alpha amino acid. The name of this amino acid is alanine. Right. Now let's look at the synthesis of beta amino alcohols. Right, beta amino alcohols. We know that there is a reducing agent, lithium aluminium hydride. So lithium aluminium hydride will reduce this CN group to CH2 NH2, right? It will reduce it to CH2 NH2 to form beta amino alcohols. Let me just rub it off. You can pause the video and write down the chemical reactions if you want. Right, all these reactions are important, and remember which is the nucleophile which is important. right, and the addition product. And remember that cyanohydrins are of great synthetic value. Right, now we'll look at the formation of beta amino alcohols. Right, beta amino alcohols from cyanohydrins can be formed by reducing it with lithium aluminium hydride. Right, this. Right, this is your beta amino alcohols. Right, now we'll look into reaction of aldehydes and ketones with Grignard reagent. Right, with Grignard reagents, aldehydes and ketones will form 1 degree alcohol. 1 degree alcohol. If we react formaldehyde with Grignard reagent, it will form 1 degree alcohol. If we react acetaldehyde with Grignard reagent, it will give a 2 degree alcohol, and with acetone it will give 3 degree alcohol. And we know that with Grignard reagents, 1 carbon atom would be increased in the resulting compound. Right, just notice that. And in Grignard reagent, which is your RMgX, right, or let's take in place of RCH3. In Grignard reagent, we know that carbon has high electronegativity with respect to magnesium. Right, so here we have CH3 minus Mgx plus. Right, so nucleophile is your methyl. Right, methyl is your nucleophile. So here your formaldehyde will react with Grignard reagent to form an addition product CH3 OMgX. Right, now this is hydrolyzed to give you an alcohol. Right, which is a 1 degree alcohol. This is hydrolyzed to give you OH. Right, plus MgOH X. So this is your primary alcohol, or 1 degree alcohol. 1 degree, or your primary alcohol. Now if we take CH3MgX, with this it will give first an addition product similar to this. Methyl is your nucleophile which will attack this carbonyl carbon, this case this carbonyl carbon. This is minus, this is plus, so this will attack at carbonyl carbon, OMgX. Now this will get hydrolyzed to give CH3H CH3OH. Now since this carbon is attached to 2 methyl groups, or this carbon is directly attached to 2 other carbon atoms, this is your 2 degree or your secondary alcohol. Right, and along with it we get MgOH X. Right. Now if we take acetone, right, with acetone it will give us 3 degree alcohol. That's CH3, CH3, right? Now this two CH3 are from this acetone. One CH3 will come from the nucleophile, will attack at this carbon CH3. Now this positive part will go to this negative oxygen, right? OMgX, right? And now this will undergo hydrolysis, right, to form CH3, 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 OH. Now this carbon atom is directly connected to 3 other carbon atoms. So this is your 3-degree or tertiary alcohol, right? I hope this is clear. And in all these reactions, just notice one thing, that here you have 1 carbon atom, but in the product you have 2 carbon atoms. Here you have 2 carbon atoms, in the product you have 3 carbon atoms. Here you have 3 carbon atoms, in the product you have 1, 2, 3, 4 carbon atoms. So when you react with Grignard reagent, it increases the length of your carbon chain by 1 carbon atom, right? So in the resulting product you have 1 carbon atom more than the reactant, right? So I hope this is clear. Now let's look into its reaction with alcohols, right? With alcohols it will form acetals, right? Ketones will not react with alcohols, whereas ketones will react with dihydric alcohols, right? Aldehydes will react with monohydric as well as dihydric alcohols, whereas ketones will react only with dihydric alcohols, not with monohydric alcohols, right? To give you acetals, right? Acetals are gem dialkoxy compounds. When we say gem, that means in gem compounds you have the alkyl groups. You have functional groups connected to the same carbon atom, right? Like we have gem diols. In that, the 2 OH groups were connected to the same carbon atom. So here in acetals that are called as gem dialkoxy, that means alkoxy group, that is OR, is connected to the same carbon atom, right? We'll just look at the reaction to make things clear. And with dihydric alcohols, the products that gets formed are your cyclic acetals and cyclic ketals. So let's quickly look at those reactions. First reaction would be your reaction of acetaldehyde with ethanol in presence of dry HCl gas. Reaction of acetaldehyde with ethanol, C2H5OH, in presence of dry HCl gas, right? So with this, first an addition product will form, right? First an addition product will form, which is this is OH would be minus, right? OH is the negative reagent which will go to this carbon. So OH here is the nucleophile, right? It will form OH and the C2H5 will come to this, right? This is your hemiacetal, right? Now this hemiacetal will again react with another molecule of C2H5OH to form CH3H. Now this H, right, this OH will abstract hydrogen or will react with H to form water, and this C2H5 will go to this O C2H5 O C2H5, right? This is your acetal, right? And this is your gem diethoxy, compound, right? This is your ethyl group. This OC2H5 is your ethoxy group, right? So this, since two ethoxy groups are connected to same carbon atom, so this is your geminal compound, right? So this acetal is gem dialkoxy compound, right? So just notice here that two molecules of alcohol will react to give you gem dialkoxy compounds with your aldehydes, right? And similar reaction take place. So as I said in the beginning, your ketones will not undergo this reaction, right? Ketones will not undergo this reaction, and from this gem dialkoxy compounds you can get back to the starting compound, which is your acetaldehyde, by treating it with mineral acids, right? Like we did before in case of bisulfides. So when this acetal, right, is treated with dilute HCl, it will give you back acetaldehyde, right? And ketones will not undergo this reaction. Now let's look at the reaction with dihydroxy compounds. This is your acetaldehyde, right, which will react with dihydroxy compounds, where you have in dihydroxy you have two OH groups, right? So the example that we will take here is your ethylene glycol. Right, you have two of these CH2. Sorry. This is your CH2, right? This is your diol. Since you have two alcohol groups, so this is your diol. That is dihydroxy. You have two hydroxy groups. We also call it as dihydroxy compounds. Right? A water molecule would be eliminated, and this takes place in the presence of PTS, para-toluene sulfonic acid. Right? This takes place in presence of para-toluene sulfonic acid. The compound that will result is CH2 right? This is your cyclic acetal. Right? This compound is your cyclic acetal. Right? I hope this is clear. And ketones also respond and undergo under similar conditions. It will react with dihydric alcohols. If I take a ketone, say acetone, it will also react, CH2, HO. This is your ethylene glycol. A water molecule would be eliminated. The same reaction in presence of PTS, para-toluene sulfonic acid. It will form a cyclic ketal. Right, this is your cyclic ketal, and the name is ethylene glycol ketal. Right, the name of this is cyclic ketal. We call it as ethylene glycol ketal. Right, I hope this is clear. Now in the next lecture we will look at those reactions where water would be eliminated, and those reactions would be reactions with ammonia and its derivatives. Right, I hope all these reactions are clear. Thanks.